Okay, let's begin our unit on similarity, Unit 7. And as we begin to talk about similarity, we're going to begin by talking about a transformation, a similarity transformation by the name of dilations. And so we'll learn how to perform dilations today and what they're all about. So to begin, we're going to take a look in GeoGebra about dilations and figure out what we notice about them as we explore the different angles uh, that occur within a dilation. So uh, as you take a look at this, you'll see that we have a slider on top here. And the slider helps us to see the scale factor as we go from triangle ABC to A prime, B prime, C prime. So as I increase the scale factor, notice the lengths of the corresponding sides. So length of 8 to 22, 6 to 16.5, and then 10 to 27.5. All those ratios give us a scale factor of 2.75 when we divide those side lengths. And then when we dilate the figure, notice what happens to the angle measures. A and A prime stay the same, C and C prime are the same, B and B prime are the same. Notice no matter how I change that up, the angles, corresponding angles are always the same in a dilation. So a dilation is just we're transforming the shape, but we're expanding it by a scale factor. So all the angles remain the same, but the lengths get changed in proportion. Here's another illustration of the dilation. And we call this a non-rigid transformation because it does not maintain congruence. So notice I can change the scale factors here. And notice our center of dilation is not on the figure this time, like it was previously. So the blue figure is the pre-image, the red is the image. Let's just take the time to take a look at some of these questions. What do we notice when the scale factor is equal to 0? So if I shrink that down to a scale factor of 0, notice we don't have a figure anymore. It gets dilated to nothing. It gets eliminated. Greater than 0 but less than 1. So notice the figure is smaller than the original when it's between those two values. When it's equal to 1, notice the figure doesn't change. Okay, it gets multiplied by a scale factor of 1, it stays the same. Greater than 1, the figure gets larger. Take the time to observe the relationship now between the scale factor and distances of the pre-image and image vertices from the center of dilation. So the images or the distances from the pre-image is 8.5, 11.2, and 13.6. The distances to the image, notice all those are doubled. Okay, what's the scale factor 2? All the distances are doubled. So if this is from D to A is 8.5, we double that and get 17.1. DB is 11.2, double that to get 22.4. Same here, 13.6, doubled is 27.2. If we change the scale factor even more, let's make it a scale factor of 1/2. Notice all these measurements are half. What about the scale factor in side lengths? 8 to 4, 6 to 3, 10 to 5. Those are all half as big. We make the scale factor 2, 10 to 20, 8 to 16, 6 to 12. All those get multiplied by 2. So hopefully you're starting to see the connection between scale factor and the properties that a dilation has. So let's kind of write that information down. So in dilations and similarity, we talked about similarity statement. Triangle ABC is similar to triangle XYZ. That would mean that angle A and X are congruent, B and Y are congruent, C and Z are congruent. And then the corresponding sides are proportional. Okay, let's describe this dilation here. FEG is similar to FDH. Describe the dilation that moves triangle FEG onto triangle FDH. So triangle FEG will be similar to triangle FDH. The center of dilation, notice that's where it's dilating from, would be at point F because it's extending out from there. And the scale factor, Scale factor, remember, compare. So F to G is 10, and G to H is 10. So total length gets doubled. So our scale factor would be 2 to 1, or it's a scale factor of 2, because it doubles in length. Okay, so that's a description of how that figure is dilated. Now let's combine dilations and rigid motions. So you can read this key concept here. If a dilation followed by any combination of rigid motions can be used to move one figure onto the other. The two figures are similar. So for instance, ABC is similar to DEF because it's a dilation. And then DEF is congruent to GHJ because it's a reflection across this line. So we could say that triangle ABC is also similar to triangle GHJ. So take the time now to take a look at these figures below and determine if they are similar. So pause the video and restart it when you're ready. Okay, so if we're trying to describe the transformations that move the blue to the red, we see that this is a dilation. It's getting larger. It's an enlargement. So scale factor is 7 to 3 because we can compare the full length, 14, and divide it by 6 to simplify to 7/3. Second example, as you go from the blue to the red, notice it shrinks. It's a reduction. So a scale factor of 2/5 because I compare 6 to the 9, and that's actually 2/3. I can't do math. And then it's also reflection across this line. So we're just combining our non-rigid motions with our rigid motions, taking what we've done before with these new dilations. All right, so let's talk now about how we perform a dilation on the coordinate plane and some of the coordinate notation that we use. So we saw how in a dilation all the lengths get multiplied by the scale factor. So if that's the case, in coordinate notation, in order to get our new coordinates, we're just going to multiply our coordinates by the scale factor. And we talked about if the scale factor is less than 1, dilation is a reduction. And if it is greater than 1, it would be an enlargement. Okay, so let's see how that works on the coordinate plane. So we can graph those original points on our graph, and we can do that by just plotting those points in our graph. So I enter A is 2, 1, B is 4, 1, oops, did that wrong. C is 4, -1, and D is 1, -1. And we can see where those points lie, A, B, C, and D. We could connect those points to have our figure. Now, our equation, or our coordinate notation we have is xy arrow 2x 2y because we have a scale factor of 2, so we're doubling both the x and the y coordinates. So in our second table, we can just take the x and the y's and just double those coordinates. So I can find my A prime, B prime, C prime, and D prime. Then by doubling all those coordinates. So I would get 4, 2, 8, 2, 8, -2, and 2, -2. And I would get those points, and I could connect those points. What do we have? 4, 2, 8, 2, 8, -2, and 2, -2. So I would see that all those distances are doubled from the origin because that is our center of dilation. So all those distances get doubled from there. The other way that I could do that would be to use a matrix. I could take my x's and y's, put those in a matrix. So I get my A, B, C, and D coordinates. So 2, 1, 4, 1, 4, -1, and 1, negative 1. Remember, in the matrix, the x values go on top, the y values go on the bottom. And all I do is I'm just going to multiply. When I multiply the matrix, I just multiply by 2 since that's my scale factor. Let's multiply all those coordinates by 2. And that would be a simple way to get the new coordinates is 4, 2, 8, 2, 8, negative 2, and 2, negative 2. So we're just multiplying everything within the matrix by 2. So determine whatever is the best way to do that for you, but you can use coordinate notation or the matrix for that. So just considering if something's a dilation, if it's a reduction or enlargement, we just look at the figure. So this is the pre-image, this is the image. So I'm going from 8 to 12. So that is an enlargement. And as we're taking a look at that, what's the scale factor? Well, we'll compare what we finished with. Well, we finished at 12, and the original was 8. So 12 to 8 is a scale factor of 4/3. If we divide those both by, oops, can't divide again. So divide both by 4 to get 3/2 is our scale factor. Okay. Take a look at the other one. Is that a reduction or enlargement? Well, if I'm going from p to p prime, notice it's getting smaller. So that would be a reduction. And can you figure out the scale factor? Scale factor would be, well, I finished at 18, started at 30. So 18 to 30. We can divide those by 6. So 3/5 would be our scale factor. Notice if we're a reduction, scale factor should be between 0 and 1. If it's an enlargement, scale factor should be greater than 1. Okay, so let's talk about how to use our compass to make a dilation. So here are the steps if we want to do a dilation with center at point D. So you want to dilate figure DEFG. What we're going to do is we're going to draw rays through each point. So we have a line that it goes through. And then we're going to take our compass, open it up, and since we want scale factor of 2, we just double that distance. So open the compass, mark off the same distance. And once we have those points marked off, we got our new figure. So let's try that. Get your compass out and play along at home. So first of all, we wanted to draw and label triangle RST. So I'm going to create a triangle. You can create any kind of triangle. I'm going to create that one. I'm going to label it RST. And we want R as the center of dilation. So I'm just going to mark that off so I see it. And then we're going to get our straight edge. Mark lines from R through S and through T. Okay. So we want those lines to extend far enough so that if we're going to dilate by a scale factor of 3, that we have enough room to do that. So next we would get our compass. See if I can find mine here. And what we want to do now is take the compass, put it on the center of dilation, open that compass up so that it extends to one of the points. So in this case, to point S. So I'll mark off the distance. Okay. And I want a scale factor of 3. So that's distance of 1, twice as long, and 3 times as long. I'll do the same thing with T. Measure off from the center of dilation. Need to shrink that just a little bit. So that's 1 distance to T, from R to T, 2 distances, and 3 distances now to get a scale factor of 3. So now that we've marked off 3 distances, we can get our points. So this is point S prime. This would be T prime. So then now if we connect those lines, so R to T prime to S prime, and R back there. There's our dilation of triangle RST with scale factor of 3. So we learned about dilations today. We learned about the properties that they have, that it maintains shape. Angles are the same, but size can be different. Corresponding sides are proportional. Distances from the center of dilation are proportional. We showed how we can describe dilations, talking about their center and their scale factor. We also talked about how we can combine dilations with other rigid transformations. And then we also took a look at how to do this on a coordinate plane by using arrow notation or using the matrix, multiplying by the matrix. And finally, we talked about how to perform dilations by hand. Have a wonderful day or evening, whatever time it is.